physics there and the other characteristics of this event mark it as a good candidate for a top quark. So that was a big achievement, noticed by the worldwide press. You know, in different languages, particle physics is over because it's gotten its last secret, or something like that. It's never over. So it was beautiful, beautiful thing that the two collaborations made the discovery at the same time. They made their announcement of the discovery simultaneously. But there was a little rivalry nevertheless. I wrote an article for our journal Physics Today about the top quark, and I sent the graphics editor of the journal a photograph of CDF and a photograph of D0. The CDF, which is on the left, you have to admit, is more interesting graphically. And so that's what they chose. And when this appeared in the mailboxes, my D0 colleagues came to me and said, how am I going to show this to my mother? So we had to have a special run of other ones made with the D0 detector in it. Okay, another wonderful aspect of Fermilab. This was started in 1980 as a daycare center, a children's center. Here are some of the kids from recent times, cute as buttons, everyone. And here's a graduation from kindergarten or preschool or something like that. The children's center has really been a great thing for our employees and also for some of our summer visitors who come with small children. It's wonderful to have high-quality care available. Okay, let's talk about another thing that we've been trying to find. We believe, on the basis of astronomical evidence and now other astrophysical evidence, it is almost certain that what we're made of makes up only 20% of the matter of the universe, or maybe 5% of the universe all told. And the other 20% of the matter, very likely, but not certain, because we haven't found it yet, is made up of a bath of particles in which we're swimming, so particle dark matter. And if it's true that we're sort of sailing on our planet and in our solar system and in our galaxy through a sea of dark matter, then if you make sensitive enough detectors, you ought to be able to see a dark matter particle bumping into normal matter now and again. And we've had a number of efforts at Fermilab trying to do this. Here's the cryogenic dark matter search on the left using electronics, semiconductor detectors. Here's a modern incarnation of the bubble chamber being used on the right. Both of these enterprises, as well as everybody else in the world, has set increasingly stringent limits on the properties of dark matter, which is not as satisfying as finding it, but is making progress nonetheless. Neutrinos have been part of the Fermilab program from the beginning. When I talked to Wilson years after he left here, he said that everything was going to be good, but he felt that neutrinos were really going to be the big stuff. A special bubble chamber, 15 feet long, was made to do neutrino physics, because you need a big target to detect these weakly interacting particles. It took pictures like the ones that we saw. Here I have a roll of the bubble chamber film. And if you look at it afterwards, roll the leader, you will see on here pictures of events induced by neutrinos and with tracks that could be interpreted. These early experiments using the 15-foot bubble chamber gave us important information about the nature of the weak interactions, especially a new kind of weak interactions called the neutral current weak interactions that were discovered in 1973 and had to be unraveled. And so were an important part of the Fermilab program. They were particularly easy to interpret, and for that reason had an advantage over some other techniques. Here's an example of one of those pictures. The reason it has all these tracks in it is that this is a mixture of helium and neon in the bubble chamber, which means that electromagnetic energy, electrons and photons, manifests itself in a jet of particles. Easy to identify. Other neutrino experiments were done from the very beginning. The first proposal, first approved experiment at Fermilab was called Experiment 1A. It was a neutrino experiment. Others as well. They had a number of purposes. One was to look inside the proton. The neutrino was a very good probe for doing that. The other was to study the nature of the weak interaction in various ways. Here's one of our later experiments called NUTEV. There's the collaboration, and the collaboration was maybe 30 or 40 people at that time. Very large, massive detectors, lots of steel interleaved with detectors. And one of the classic experiments at Fermilab was to look for a new kind of neutrino called the tau neutrino. This is another one of those particles whose existence we inferred from other experiments. And we could say what its properties would be, but it's still very satisfying to show that it's really there and behaves as expected. So we thought that the tau neutrino, which we figured out how to make in a complicated way, when it interacted with normal targets, could make something called the tau lepton, a very heavy friend of the electron, which itself decays in about a trillionth of a second. And so if you could see nothing coming in, namely the neutrino, an interaction, and then a particle that decayed in the space of a few tenths of a millimeter or a millimeter, you would be able to do that. And a very effective way of doing that was to use photographic emulsion, which has very high spatial resolution. It has the disadvantage that you have to take it out and develop it before you can see what's there. And then you have to know where to look in a very small space in a very big place. And so you want to make a hybrid detector that has the ability to point back to the right place in the photographic emulsion in order to see the events. So these people, the donut experiment for direct observation of new tau, made such a detector which had emulsion targets interleaved with something called scintillating fibers, which are shown here. They respond very nicely to radiation. And then conventional detectors downstream. And they were able to find a few examples of exactly what was expected. So what you see here is some interaction. Let's look here at the top. An interaction making a few particles, one of which goes a few millimeters, actually, and then has a kink in which it's decaying into something plus neutral stuff. And these other three examples also show that. So they demonstrated for the first time that the tau neutrino was not just a figment of our imagination, but was real. And this has now developed a technique that people have used to probe properties of neutrino oscillations, one kind of neutrino changing into others. The next step in accelerator development, both for the good of the Tevatron Collider program and for our current and future program of neutrinos, was to replace the main ring. It was primitive by modern standards, and also had the annoying feature that one piece of the main ring actually went through the D0 detector. So it's like having a piece of an accelerator in the liver of your detector. So it was moved to a new place, 1 pi kilometer around, just out the back. Main injector is on the bottom here, and on the top is a novel storage ring made of permanent magnets instead of electromagnets. And so with very low operating costs, quite a clever innovation. And this has allowed us not only to increase the number of protons and antiprotons that we put into the collider during the days when it was operating, which gave much greater capability to CDF and D0, and also to put unprecedented amounts of proton power onto the targets that make neutrino beams for our current round of neutrinos. So one of the highlights of our current program is to send neutrinos through the Earth. We bend them down by about 3 degrees, send them through the Earth, and they come out at the Sudan mine in northern Minnesota, where 2,400 feet or so underground, there is this magnificent object. The detector is there. It's about 8 meters high. So again, it's massive because neutrinos interact very little. The flux of them reaching a distant place is small. They are lucky to have this magnificent mural in their mine site. So this experiment has told us a great deal about the properties of neutrino oscillations. We make them here mostly as muon neutrinos. By the time they arrive there, some of them have changed into electron neutrinos or tau neutrinos. And this is really on the leading edge of neutrino physics today to understand these properties. A second newer experiment, also in northern Minnesota, is called the NOVA experiment. Here it is as it's being set up. It's also in operation now. This is on the surface. It's in a building that's as long as a football field, roughly. And you can see that the detector is about 4 stories tall. So these are big detectors in order to register what's happening at the other end. So just a few words about things that we've been doing that don't involve directly terrestrial accelerators. In 1941, Pierre Auger, who was one of the founders of cosmic ray physics, wrote a book translated into English with the title, What are Cosmic Rays? My colleagues are still asking this question, even though we've learned quite a lot in the intervening time. And the contribution of Fermilab and its collaborators to this subject has been to go from sort of cottage industry experiments to really big experiments. A really big experiment we have in mind is one that is actually conducted in Argentina. But if I put the apparatus, the array, center it on Fermilab, it looks like this. So it's a considerable installation. There's 1,600 ground stations and 5 stations that look up at the sky. Here you can see a cartoon of a cosmic ray, or a proton or something coming in from way out there, interacting in the top of the atmosphere, making a shower of stuff, electrons and photons and so on, muons that come down to the bottom. Those are detected in the ground stations, but then you can also look up and see the air fluorescing as the burst of energy goes through it. So that's having 2 techniques to look at these things is one of the great features, in addition to the wide area that they cover in this case. Here is a Google Earth illustration. So you see a few houses over here being illuminated by muons and other things. And then the fluorescence detectors looking up and seeing a piece of track here, a piece of track there. And from that they can reconstruct in 3 dimensions the trace of the cosmic rays and shower that came into their detector. So that's been a very productive experiment. One of the things that they've done is to measure the number of particles that reach us at stupendously high energy. The energies they're considering, the rate of cosmic rays, primary cosmic rays, is about 1 per square kilometer per year, something like that. That's why you need a big detector and a lot of patience. And what they found is that as you go up above around 10 to the 19 electron volts, a little bit more, flux of cosmic rays abruptly falls off. This was predicted because the universe at large is filled with cosmic microwave background radiation, the famous 3-degree radiation. And if it's really there, we know it's there, and protons of higher energy come along, they will hit the cosmic microwave background radiation and make pions by a process called photoproduction. And so there should be a cutoff at exactly this place in the spectrum. So that almost is a proof of the cutoff that's there as expected, but what remains to be shown is that there are actually sources of protons of energies higher than the cutoff would tell you, and that's the next step in the research. Another intriguing thing that they found is the change in the composition of cosmic rays as you go up in energy. It looks like they're changing from protons to heavier nuclei as you go up. That's still work in progress and hasn't been sorted out. Anyway, the industrialization of that kind of research has really led to new insights. We've done some astronomical research. So the first is the Sloan Digital Sky Survey, and I'll just show you why it matters to be able to do big things. Here are 500 different supernovae observed in the Sky Survey. These are then followed up for study by the Hubble Space Telescope and other instruments. Here is a couple slices of the sky showing this filamentary structure in the stuff out there, the galaxies out there, again taken from the Sky Survey. And here is our most recent astronomical enterprise, the Dark Energy Survey in Chile. Here just one little illustration of what they've been doing. They and their colleagues have discovered some things called dwarf galaxies, which are satellites of our own galaxy, but are smaller and darker than the ones we knew about before. It's an illustration that our senses are limited, our instruments are limited. When we make improvements in our instruments, we discover new things. Here, by a technique using spectroscopic information, they're able to get rid of the foreground and to see the dwarf galaxy by itself. That's one nice little piece of work for them. Okay. So, two last things to talk about. One is our participation in the Large Hadron Collider at CERN. There have been two elements of this. One is to build pieces of the accelerator, in particular the magnets that bring the beams into small spots and give high collision rates. So a number of those are fabricated here at Fermilab by my colleagues. They look like big things, but they take a lot of meticulous work. The LHC, the Large Hadron Collider at CERN, is bigger than our machine. It's 27 kilometers around, or 17 miles around. The CERN laboratory is this little triangle. That's the LHC. It's about 100 meters underground. I always tell my friends from CERN, you know, they've got this nice little airport. We've got a much bigger airport. They've got this cute little lake, and we've got a much bigger lake. They have the Alps. Anyway, there are two main experiments, and Fermilab is the United States headquarters for this CMS experiment, which lives over here. Their friendly rivals, the Atlas experiment, lives here. And in this accelerator, which has about 7 times the energy of what our Tevatron had in its heyday, protons and protons collide head-on, and people have done great things, including, so here's the CMS detector that my colleagues participated in. Big and brawny, it's 4 or 5 stories high. Lots of steel and muscle, and also superbly fine electronics that you see here in the silicon tracker. This itself is about 4 meters in diameter. And these people, as you will recall from the 4th of July in 2012, together with their colleagues at the Atlas experiment, discovered the Higgs boson and gave us new insights into the nature of the origin of mass, the way that weak interactions work, and so on. And they have been involved in a new run of the accelerator at somewhat higher energy than 13 TeV. Just today, our CMS colleagues are switching out some of their central tracking apparatus for an improved apparatus, and we expect more great things from them in the near future. Okay, what's happening at Fermilab now? In the future, we're moving on with a suite of experiments. This is from the Microvoon experiment, one of their first neutrino events, in a new kind of detector for us to use for neutrino research. It's called the liquid argon time projection chamber. It serves in some respects as a prototype for what we hope will be the new gigantic experiments that we'll do in the future. And they're off to a running start. This gives pictures of total chamber aspect, but of much finer quality, telling you about the characteristic of the particles that are emitted and allowing you to say things quickly, electronically, and in great detail. So that is off to a great start. We're building muon experiments just behind us here. On the left, just behind the booster, you see the muon magnetic moment building. That's completed, and I'll show you something inside it. And then this is a somewhat old picture from last year. The building being completed next to it is for a new experiment that will look for extremely rare, we think, disintegration of a muon into an electron, or transformation of a muon into an electron. Here is the magnetic ring for the muon magnetic moment experiment. This is a few months ago. They've done a lot of work in getting it ready for data taking, and maybe by the end of this year or beginning of next year, they will begin taking data and give us answers after that. After that, the big deal that Fermilab has involved is to send neutrinos not just 500 miles to northern Minnesota through the Earth, but 800 miles to South Dakota, to the bustling village of Lead, South Dakota, where there will be very large underground particle detectors, and we hope to elaborate the mysteries of neutrino oscillations and other aspects of neutrino physics by doing that. So when I came here to Fermilab for the first time, I was at a university. It was a great place. The whole future before me when I came here, and this was I soon learned, the most exciting place I could imagine being, and I'm hoping that it will be made for other young people the most exciting place to be. My colleague John Peoples, when he was director, liked to say that at Fermilab we make things and they work. And if you look at these pictures, I would amend his statement to say that our colleagues make very beautiful things and they work. Thank you very much.
Welcome to Fermilab. I'm Josh Freeman. No, I'm not at all Josh Freeman. I'm actually the guy standing between you and Josh Freeman just for a couple of minutes. My name is Andre Salles. I work with the Arts and Lecture Series Committee here at Fermilab. We're the group that picks the art series and lecture series performers and speakers, and it's a privilege to do so. Just wanted to tell you a few things that we have coming up if you're interested in coming back, as I hope you are. So on Sunday, this weekend, if you want to make a weekend of it, we have the final concert in our Gallery Chamber series for this year. The Gallery Chamber series is a bunch of intimate concerts that take place in the art gallery upstairs. And Sunday's concert features Jennifer Gunn and Tim Monroe, a pair of flutists. They'll be playing separately and together. Should be a very good show. That's at 2:30 p.m. on Sunday. On Friday, April 8th, Dr. Phil Mote, I think it's Mote, I'm going to go with Mote. Dr. Phil Mote of Oregon State University will be here to talk about climate change. His talk is called 5 Things I Wish Were True About Climate Change. So that's on April 8th at 8 p.m. On Saturday, April 23rd, we have the Stars of Dance Chicago coming to perform on our stage. That's a number of different local dance troupes that perform a variety of different types of dance. Always a good show. That is also at 8 p.m. on Saturday, April 23rd. And I've been asked to mention we have a brand new lecture that's just been added to our calendar. That's on Wednesday, June 15th, special day. It's Barry Barish of Caltech, who will be here to talk about the recent discovery of gravitational waves by an experiment called LIGO. Hear that? Yeah, that's exciting. So his talk is entitled Einstein's Black Holes as a Cosmic Chirp, which is a great title. So those tickets are actually on sale on our website now. The Arts and Lecture Series website is snal.gov/culture. A couple other things I wanted to mention. If you have not been upstairs to our art gallery today to see the exhibit called Art of Darkness, that is all images from the Dark Energy Survey and of the observatory where that takes place, you really should. After the lecture, you're welcome to come upstairs and look at it, and the art gallery is open Monday through Friday, 8 a.m. to 4:30 p.m. if you want to come back. Some of you may know, we, in addition to all of the lectures and art series events that we put on here, sometimes we moonlight as a particle physics laboratory. We do some science. It's pretty cool. We're always willing to answer questions about that. We have a new brochure that I would love to see you all take home, full of pictures and information. And we have a free public tour every Wednesday at 10:30 a.m. So on to tonight. I should mention tonight's lecture is completely sold out. We have a totally full flight. So thank you. Thank you all for being here. Very much appreciated. The speaker tonight, he's a professor of astronomy and astrophysics at the University of Chicago. He's a senior scientist at the Theoretical Astrophysics Group here at Fermilab. He got his PhD in physics from the University of Chicago. He's been at Fermilab since 1988. He was the the head of the Theoretical Astrophysics Group from 1994 to 1999. He led the Sloan Digital Sky Survey Supernova Survey, which discovered more than 500 supernovae for cosmic study. And he is a founder and current director of the Dark Energy Survey. Ladies and gentlemen, Dr. Josh Freeman.
Thank you, Andre. Can you hear me? Good. I want to add my welcome to Fermilab, and where we'll be spending the next few hours talking about the dark universe. It's a big universe, lots to talk about. So to set the context, though, I want to start by reminding you of a few basic facts about the universe that I think everyone should know. So the first fact is that the universe is very old. Anyone know how old the universe is? 13.7 billion. Good. All right, this is a good audience. Yes. You've been reading ahead, or it's older than Bernie Sanders, either way. That's it for the political jokes for the night. So it's actually 13.8 billion. It's gotten older. So how do we know it's old? Well, there are a number of things. It contains old things in it. The Earth, we know, is about 4.5 billion years old. The Sun, about 5 billion years. The oldest stars in our galaxy, about 13 billion years. And most recently, observations of the cosmic microwave background that we'll talk a little bit about later have pinned it down to this 13.8 billion years. So this is just an example of some of the oldest stars in our galaxy. This is a globular star cluster, Omega Centaurus, an image taken by the dark energy camera that I'll be talking about later, of stars that are about 13 billion years old. Second basic fact about the universe, it's very big. I'm not going to ask how big it is, because it's really big. So the most distant objects we can see are about this many miles away. That's a lot of zeros. I think this is 100 zettamiles if you look it up. And of course, when we get to such large distances, miles are not a very good unit of distance because it's just too many zeros to keep track of. So instead, we use the fact that light travels very quickly, 186,000 miles per second. So in 1 year, light travels 6 trillion miles. So that defines the unit of distance, the light year. And so this many miles, that many zeros up there, corresponds to about 30 billion light years. So that's the most distant things we see are about 30 billion light years. And just to set the scale, the Sun, our nearest star, is about 8 light minutes away. The nearest other stars near the Sun are a few light years away. So the universe is very big. Third basic fact is the universe contains billions of galaxies in it. So if you travel galaxies with the naked eye. So just a little quiz. So this is a galaxy that we can actually see from the northern hemisphere too. Anybody know what this galaxy is? Milky Way. Very good. All right, this is very great. Does anybody know what that galaxy is? Oh, wow. Right. Small Magellanic Cloud, that's right. And this is the Large Magellanic Cloud. These are two dwarf galaxy satellites of the Milky Way. You can only see them from the southern hemisphere, not from the north. So if you ever do go down south, I urge you to go out in a dark night and see if you can see them. It's quite spectacular. So these are examples of nearby galaxies, and the universe is filled with billions of these galaxies. This is a more typical galaxy, and they're typically about 60,000 light years across, contain tens of billions of stars, and they rotate like this galaxy, like our own Milky Way, rotates around its center with on an average, takes about 200 million years. This is also an image taken with our. So if we can bring the lights down just a little bit, I want to show you a few examples of some pretty galaxies that we've taken pictures of with the dark energy camera. This is NGC 253. I'm sure you all knew that. In the constellation Sculptor. And this is, of course, the familiar NGC 1566. Also, these galaxies are a few tens of millions of light years away. So galaxies, with their billions of them, they're all around the universe, but they don't exist in isolation. They live in and are shaped by a variety of environments, and in proximity to other galaxies with which they occasionally interact. So sort of like my teenage daughters occasionally interact with me, galaxies occasionally interact with others. Sometimes you find them in pairs or in groups or in clusters of tens to hundreds of thousands of galaxies. And those in themselves form part of a larger cosmic web of structure. We used to call these superclusters. So this is just one example here I pulled out. NGC 1672 is a nice large spiral galaxy in the foreground. But if you look down below here, you see a number of more distant, therefore they're smaller galaxies in a group of galaxies, which is sort of a hint that these galaxies are not just randomly distributed out space. They cluster together. There's NGC 1703 in the foreground, but if we look a little closer, if you look on the right of that galaxy, again you see a lot of these smaller yellowish galaxies. That's a more distant cluster of galaxies that happens to be behind this foreground cluster. So galaxies clump together into pairs, groups, and clusters of galaxies. This is a cluster of galaxies. Another image taken from the Dark Energy Survey. Again, all those yellowish galaxies are all in a relatively small volume of space, that being a few million light years across, and they cluster together. This is a very famous cluster of galaxies. This isn't an image from our survey. The Coma cluster of galaxies. Again, clusters are sort of the largest gravitationally bound systems we know of in the universe. Again, a few million light years across. And they contain about 1 quadrillion times the mass, so 1,000 trillion times the mass of our sun, typically. And again, that's composed of tens of thousands of galaxies. Now, Coma is an extremely important cluster of galaxies historically, because it was studied by this character, Fritz Zwicky, was an astronomer at Caltech in the first part of the 20th century. As you can probably tell from the image, Zwicky was quite a sort of irascible character. He was quite an eccentric personality, but he was also a pioneer of much of modern astronomy. He was one of the first to carry out really major surveys of galaxies. He also is the discoverer of dark matter, as we'll talk about in a minute. Postulated neutron stars, did the first real quantitative studies of supernovas. And in the 1930s, Zwicky studied the motions of galaxies within that Coma cluster. He measured how fast the galaxies were moving with respect to us within the Coma cluster. And he found that those galaxies were moving remarkably fast, of over 1,000 kilometers per second relative to each other. And that was just simply too fast for them to remain confined by the gravitational field of the other galaxies in that cluster. So this is the puzzle. Why is the Coma cluster still there? Why haven't those galaxies all just streamed away from each other if they're moving so fast relative to each other? And so what Zwicky postulated was that the Coma cluster, in addition to the luminous galaxies we could see, that Coma was filled with dark matter. And that the gravity of that dark matter, the material that we can't see, must be the thing that's keeping the galaxies within the Coma cluster from flying off into extra clusters. So he really was the first one to study this concept in detail, and concluded that clusters of galaxies are mostly made of dinosaurs. So an image like this, where we think we're looking at clusters, we're really looking just at these galaxies that are kind of like sprinkles in this vast ice cream of dark matter. And we know the dark matter is there because it exerts this gravitational pull on the galaxies that we can see. All right, now let's skip forward, and using Einstein's theory of relativity, I'll remind you that Einstein reinvented our notion of how gravity works through the concept that gravity is not just a force between two massive bodies. Instead, massive bodies or any kind of energy occurs in space-time in its vicinity case of